Chapter 33 is on three-phase motors. There are three basic types of three-phase motors, and we are going to spend all of our time really talking about the squirrel cage induction motor. There's a picture of one over here. Advantages: low cost, definitely very simple construction. These things are used all over the place. They're very robust, and they're just used in so many different applications. A second basic type is the wound rotor induction motor, which is difficult to say. We will not be covering this motor in great detail, but just so you know, it's one of the three basic types. And you can see the advantages here: high starting torque, low starting current, and we can control the speed very well with these motors. And then finally, the third basic type of three-phase motor is the synchronous motor. Again, we will not be covering this one in any detail. Picture one here. Definitely great for high horsepower applications. And this is kind of a key one here: constant speed from no load to maximum load. So the load that's what the motor is sort of turning or twisting. So if you have no load, or whatever the maximum load that motor is rated for, that motor will give constant speed. All three-phase motors operate on the same principle. That principle is a rotating magnetic field. There are three factors that cause the magnetic field to rotate. These three factors will be on the final, so you may want to take some notes here. Factor one: the three voltages in a three-phase system are 120 degrees out of phase with each other. Two, the three voltages change polarity at regular intervals. That, by the way, that's our AC voltage that we know. And then number three is the arrangement of the stator windings around the inside of the motor. To really get a good sense of this, I have a link in D2L to this video. How does an induction motor work? I highly recommend that you watch that video, and you may even want to watch it a couple of times. Three-phase motors all operate on the principle of a rotating magnetic field. The speed at which that field rotates, that's called the synchronous speed. And this is important. You might want to take notes on this. And there are two factors that determine the synchronous speed. You see them here: number of stator poles per phase and the frequency of the applied voltage. These will definitely be on the final exam, so again, take some notes here. And also on D2L, I have a link to this video here, how three-phase motors work. Have a look at that video and take some mental notes when you're watching. Squirrel cage motors have different parts. If you watched that one video I referenced in the last scene, you will have seen those parts. Here is a drawing of them. This will be on the final, so make sure you take some notes here. The parts that I'm particularly interested in: so there's the stator. That's this piece in here. Stator, stationary, it doesn't move. It has coils of wire in it. The second major component I want you to remember, that's the rotor. So the name rotor, rotate, rotational. This actually moves. It actually spins inside of the stator. Magnetic induction from the stator causes the rotor to rotate. The motor frame, another key part, that basically protects the motor here. So inside of the motor frame you have the stator. Inside of the stator you have the rotor. The rotor actually goes in there. And then finally, the other key component I want you to remember for the final, fan blades. This is a moving, rotating machine. There is friction, so heat is generated. So these fan blades here, they're on both sides of the rotor. As the rotor spins, the fan blades cool down the motor. We're going to look closer at how a squirrel cage motor works. When we first apply power to the motor, literally at time 0, the rotor is not turning. But as soon as we apply power to the motor, the rotating magnetic field inside of the stator is created. The speed of that rotating magnetic field is synchronous speed. And let's say, for example, in this particular motor, synchronous speed is 1800 RPM. This means that the magnetic field inside of the stator is cutting the rotor at 1800 RPMs. That cutting action induces a voltage into these rotor bars. If you recall from way back earlier in the course, there are 3 factors that determine the amount of induced voltage, the amount of voltage induced onto these bars. The strength of the magnetic field, the number of turns of wire cut by the magnetic field, and the speed of the cutting action. Inside of this motor, the strength of the magnetic field remains constant when power is applied. The number of turns of wire cut by the magnetic field, that is determined by the number of these rotor bars. That too remains equal. What does change in the motor is the speed of this cutting action. So at time 0, synchronous speed 1800 RPM, magnetic field turning at 1800 RPM. At time 0, the rotor is not turning, it's literally stationary. So the speed of the cutting action at time 0 equals 1800 RPM, that's synchronous speed, minus 0. This 0 is the speed that the rotor is turning. So we have the highest speed of cutting action. When the rotor is not turning at that time 0, that cutting action is at its fastest. This means that the induced voltage is at its maximum. That maximum induced voltage causes a current to flow in these rotor bars. And if you watch those other videos that I talked about, you'll understand what I'm talking about. The maximum voltage, induced voltage, equates to a maximum or very high rotor current. The rotor current inside of the rotor creates a magnetic field in the rotor. And this rotor magnetic field is attracted to the stator magnetic field. So the magnetic field in the rotor is interacting with the magnetic field inside of the stator. That's what's causing the rotor to turn. As the rotor turns, as it accelerates, the cutting action slows down. So let's say, for example, after, let's say 2 seconds, time 2 seconds, let's say that the rotor speed has accelerated to 600 RPM. So at time 2 seconds, the cutting action is 1800 RPM minus 600 RPM is 1200. That's the new speed of the cutting action. So it has reduced from 1800 to 1200. Remember that the amount of induced voltage is determined by the speed of that cutting action. So the slower cutting action means less voltage is induced. Less voltage means less current in the rotor and the stator. As time continues on, the rotor accelerates and accelerates, and it keeps going faster until it reaches nearly, but not quite, synchronous speed. If the rotor did reach synchronous speed, that would mean the cutting action would be 0. 1800 minus 1800 is 0. Therefore, there would be no induced voltage. The difference in synchronous speed, 1800, and rotor speed is called slip. I'm going to write that right here. And I'll have on the next slide a little bit of math that goes over slip. But for now, remember that slip is the difference between synchronous speed, which is 1800, and this nearly synchronous speed, which is our rotor speed. We know that the rotor can never reach synchronous speed. If it did, there would be no cutting action, and then the rotor would stop. So the difference between synchronous speed and rotor speed is slip. The formula to calculate the percent slip is given here. Synchronous speed minus rotor speed divided by synchronous speed. So in our example, synchronous speed equals 1800 RPM. Let's say that our rotor speed, once it reaches its maximum speed, let's just say that it's 1725 RPM. So the percent slip equals 1800 RPM minus 1725 RPM divided by 1800 RPM equals 4.16%. If you do this math, by the way, on your calculator, you would get 0.0416. 4.16 is the percent equivalent of this decimal number.